All right, gentlemen, we're live.
Thank you. I hope everyone can hear us fine. I'd like to thank you for joining our panel discussion today on innovation in construction. We're going to be showing you how turning the building construction process on its head is going to save both time and money and bring about other benefits to the healthcare delivery process. We have a panel today to do that. I'm Edwin T. Dean with IMEG. I'll be moderating and leading you through the discussion with the other gentlemen on our panel. Joining us today is Jeff Grillo with TGE Top Down. Jeff's background is representing major industrial high-tech manufacturer with a responsibility for billions of dollars of construction annually, and he's going to represent the owner's point of view. Also on our call is Dan Esparza with TGE Top Down. His background is managing general contractors and representing the builder's point of view. And our third panelist is Charlie Thornton with TGE Top Down. His background is as an icon in the structural engineering community, and he is the founder of one of our nation's largest engineering firms, and he'll be representing the engineer's point of view. Our next slide here is talks about what we're going to discuss, and let me just give you a real takeaway. What I hope you come away from this presentation, because there's going to be a lot of material at you, but understand that innovation is transformative, and innovation comes at you not in incremental pieces, but by taking a step back and rethinking the problem and coming up with a unique solution. I think all of us interact with technology today, and if you think about the technology that we have and what we might have had 20 years ago, you may not have even imagined it. So what you're going to see today, I hope you can see as innovative, because it is transformative and it takes you away to a different place than maybe you've thought about how to do construction and how we can save money and save schedule. So let me turn it over to Dan. We have a couple quick videos here to show you, to illustrate what we're talking about. Dan?
Appreciate it, Ed. Thank you so much. As Ed mentioned, I'm Dan Esparza, and I'm going to run through just real quickly. I spent a lot of time on get this going. This is a representative example of the system. It's kind of a real quick overview. And hopefully this, I always say a picture is worth 1,000 words, but this is a comparative analysis of our system, the top-down system, and it's really a learned system, a structural system. And Charlie will speak to the engineering of the core and shell advantage of top-down versus a conventional built system. And so what we really wanted to do was to kind of start off to show the innovation model and the new technology, but not just from an engineered solution, but from a construction delivery model. And so what we'll talk about it today a little bit is the learned environment from an owner's perspective, from a build perspective, and an engineered solution perspective. But I think it really, the holistic model and how it impacts healthcare and other asset classes, but I think it has a significant impact to healthcare and tall building structures for healthcare, is how we can increase efficiencies with time and specifically cost and sustainability. And so what we really wanted to do was to start off with this, because obviously the comparative analysis captures the entire model. It kind of gives an overview of the delivery model and the process. And so you can see how the build comes together. It eliminates the tower crane. It's a manufactured process at ground level. It's built basically in compression and shear on the core, and everything is a structural design system that is core focused. And so we'll talk to the engineering aspect through Charlie's presentation, but really wanted to focus on the comparative analysis and how the build comes together. So I think this is a representation that speaks to that at a high level, and then we'll kind of dive into the weeds throughout this presentation. So this kind of gives an overview of the technology from a delivery perspective as a building model. A previous project that we completed in the commercial space is represented in a project that we did in the commercial A lab office. which was done this is a 624,000 square foot, 10-story lab office space. And actually, Jeff, in his presentation next, is going to actually go through the metrics on this build. But this is a turnkey operation from a core and shell. This was completed about 2 years ago for a major Fortune 500 client. And it is the metrics on this we'll talk about here in a little bit. But again, core development, core and shell, compression and shear on the core, and everything built at ground level. This was an internationally built project. Some of the project items that we would do domestically here in the U.S. would be a little bit different. But again, a more manufactured build, everything at ground level, roof construction, built first, strand jacks at the top, and on a very repetitive basis. And so what we're looking at is decreasing the scheduled time and a vertically integrated supply chain. And so we're really changing the innovation model from the design application to the build application and bringing that to a turnkey process. And so as you look at how projects are taking longer, especially in healthcare, I think the complications in projects, as you go taller, buildings become less efficient. We're looking at more innovative strategies, a learned environment to look at things differently. We want to make sure that this type of building application gets some better visibility. So with this project, again, 624,000 square feet, 10-story build, a very manufactured building process at ground level. And we'll talk a little bit more about the building applications here in a little bit, but wanted to kind of give a real world, a real case analysis of the structure as it's developed. A lot of manufacturing, prefabricated elements go into this build, and are able to capture those efficiencies of on-site, off-site construction, and the industrialized process that goes into the build. So we can interplay that from a design, manufacturing, fabrication, and construct model. And so that's all vertically integrated into the process of a top-down delivery model. So those are the innovation processes that we're wanting to present as a new technology delivery format, and provide a little bit more visibility on the technology in the construction space, specifically for tall buildings, and how we solve some of the current challenges in the market on complex projects. So with that, I'm going to turn it back over to Jeff, talk a little bit more about some owner applications in the market and where the industry performance metrics are.
Jeff, you're muted.
I will start once again. Thanks, Ed. So as an owner, we used to call this either the what we could buy from the construction industry or what our challenges were in the construction industry. We worked for, in the upper left is the productivity, comes out of BLS, and unfortunately what I represented inside the owner was construction, which was one of 3 negative productivity businesses over the last 60 years. But I worked for companies who were on the top of that curve. So they were looking at and couldn't understand why we were getting no productivity gains in the industry we represented. Over on the upper right is we tried every contract method known to mankind. We got incremental improvements on some of them, but claims and delays ended up they were a continuous problem. On the lower left, this comes out, you can pick up any construction industry literature and see that the bigger the project gets, usually the further behind it is on delayed being completed, and as what the amount is over budget. We experience this over and over again. Our companies expected us to be very predictable on what our cost and time was. Unfortunately, the industry doesn't deliver that. And on the lower right is most industries, you have to innovate, which means you have change during your design and construction. The construction industry is extremely inflexible to be able to pick those up and incorporate those without large impact. So these were always the big 4 challenges we were looking at, is how do we go solve them. So go to the next page, Dan. So what it took to solve it was really looking in the mirror, and we had to recognize that we were actually part of the problem. We didn't like to admit it. We were a pretty big part of the problem. So we turned inside and started looking at, we worked for companies who were on the top of that productivity curve or predictability curve. Every year they were pushing out more product. Again, I worked for Intel, was one of those. When I started, they used to put 1 million transistors on something the size of your thumb. And when I left, they were doing 10 billion on the size of your thumb. The one that was 1 million cost about $1,000 a chip. When I left, it was $200 a chip for 10 billion transistors. So, you're working in industries who are innovating and they have to do more for less. Construction was in a different perspective. So when we looked at them, there was a plethora of items we needed to go improve. But it really boiled down to us. What was making them successful in those spaces were they were getting out of the transactional relationships and moving to partnerships. In our world, that was how do we go take the designer, builder, trades, vendors, and stop making them working against each other and make them work together. And eliminate that learning curve of bringing in a new team every time we went and did, another project. The second one was how did we go take those concepts of bringing manufacturing to construction? We went out, we did a pretty big survey out there of just about everything. We went over, looked, there was some things in Asia that were being done around modularization. We looked at the boxes that were being done, modules. When we went through it, the only one that came down with it was going to meet all our needs was top-down construction. So Dan just showed you the video. I'll walk you through a few of the metrics of the projects here on the next page. So we started this. We've gone out. We had a traditional design done. We went out and bid it. We were floored when we got the cost. The project was in Bangalore, India. We were just looking at this modularization and how do we go improve it. We met Charlie. We decided we were going to go give it a shot. We did building one. This is what we call our innovation 1.0. At that time, the building had been built, I believe it was about 40 years, Charlie. So there was some time to sort of dust it off and bring it up to the current construction efficiencies that were out there today. We went off and did that. We ended up completing it and still in less time, even though we had to go do a ground up design on it and build it. We were still less time than where we would have been if we would have kept doing the traditional path that we were on. So we saved at that time, we went from a 30-month construction down to about 20. And we took about 20% of what we call the total value out, and I'll cover that in the next page. The company couldn't believe it. We actually finished it a little earlier than what we told the company. We were actually below budget. It had been years since we had a project that turned out that way. To the point they decided we were going to go build another one. We turned around and built the second one. On this one, we turned around and we got the full cycle time down to 20 months from design through people moving into the building. And we were 40 months on the traditional. So our initial goal was to cut it in half. We did cut it in half. And we got about another 5% cost efficiency out of that one. And I think we've ended up with a list of items. And on the next one, we'll be able to repeat that. So again, like Dan said earlier, we call it a learning system because when we went and did the next one, it was the modularization of this building enabled us not to have to go redesign the whole building, even though there were a number of differences that we had to go do with the building. And like I said, the speed of that, the AHJs were looking at it and they were accepting it much faster because they understood the building system. It wasn't going and approving a custom design. And one of our big problems was every time we changed the height of a building, we started over again because the structure and foundation had to be redesigned. On this building, there's almost no redesign, go as high or low as you want. And 90% of the design stays relatively the same. So next page, Dan. So, we step back and we look at the value propositions. When we first looked at it, we were like most owners and said, how much cheaper is it to go build this building versus the other building? When we took a step back and looked at it, not only was the initial construction cost cheaper, but whether you're financing it, which we do with some client, who we work with do financing, we financed our own, but it was the working cost of capital. We took a look at the ability, we increased the space. I think on that one, Charlie, we were 5 to 7%. We picked up no difference in footprint, but because of the open and columnless design, we gained 5 to 7%. And plus, I'm sorry, Charlie.
A 10% increase in headcount.
Yeah, so that's kind of how we measured it is. We weren't on the space, but we got 10% more headcount in the building, which is what mattered to us as the owner. from a quality perspective, flexible space, the optimization of labs, Intel actually ended up relocating a whole bunch of labs over there because they were able to gang them up and configure them in ways that you couldn't do inside a traditional building. And then for folks that are out there that are doing more commercial buildings, it gives them a premium space where you have these clear views and you have that flexible design and setup inside your building. And we've done these studies for a couple commercial buildings where they're seeing 10 to 20% increased either rental rates or sales rates based upon the flexibility and the type of space. On schedule, again, about half the time. For us, that meant that we were saving over $1 million in leasing fees, plus we were getting revenue out faster. And then finally on safety, Intel was huge on safety. We wanted to make sure everybody went home as good or better than when it came in that morning. We had one recordable, and it was a small cut over 5 million man hours. That was in India, where safety rates are typically fairly low. And unfortunately, the last high rise we had done before this, we ended up having 2 fatalities. So the safety of the system where everything gets done on the ground was amazing, and it showed in the safety. So again, as an owner, this was one that checked every single box. We got predictable. We had continuous improvement. And it was continuing as forward. So it got to the point where we decided we were going to get out of the office building business for a while. And so my testimony on how this works is I decided then it was time to go leave Intel, and that's how I joined Charlie and Dan to form TGE. So it's truly a building system that from an owner's point of view checks all the boxes. And I'm going to turn it over to Dan, who's going to walk you through the construction.
Thanks, Jeff. Appreciate that. So, obviously one of the biggest challenges I think we have in our industry is innovation. And I think, the movement in where we're at for our entire industry in the AE space is innovation and where we're going. And I think this slide just pretty much is representative of where we're at in the tall structure spaces about where, I think it's just kind of, I think it's a good representative image of tall structures. And whether you're looking at steel and or CIP type structures, and what we look at in terms of the asset class for the different building types on the vertical. And what top down is able to do from our building technology is really address a lot of the challenges that I think the current state of construction is in. Capital projects are taking longer, they're costing more, and that's a consistent trend year over year. And the challenges for tall structures, as the height increases with 30% less efficiency on the structures, we're really focusing on where those current state challenges are really impacting the build. Not just with the inefficiencies of labor, and the inefficiencies of supply chain dynamics, safety, quality control, the ongoing challenges that the market continues to be plagued with. And those are the things that I think top-down excels at because of the predictability and the lean nature of how we brought our, the building process together, but the engineered delivery of the building and then how the building is actually delivered. So I'm sure a lot of you guys, a lot of the folks here on this are well versed in what the challenges in the state of construction are. But again, they continue to rise on a year-over-year basis, and we're not improving. And I think Jeff spoke to that in terms of the slide earlier about where our industry performance is really not gaining any advantages. We're getting some technological advantages in terms of some software, but we're really not changing how the building gets built. This is a truly revolutionary process in terms of how we can change the advantages of core and shell and lean out material by mass. If you look at the structure for top down, what we're doing is, and Charlie will speak to this, is leaning out the material by mass, because the elimination of columns reduces the element of work. We're taking out actual structure. And so that can reduce the labor component, the material component, and increase efficiency of the build, plus we're building at a ground level. So a lot of advantages in that process for actual construction. But I think from a building process and how we learn as builders and in Lean and Last Planner and the application of building this as an integrated building supply chain process is all of the advantages that come from top down because it's a delivered engineered solution. Is we're eliminating a tower crane, which has a huge cost impact to the project. There's no retooling of trades. It's all standard application of the delivery model. We can erect a standardized floor plate at ground level and continue that one floor at a time. And that repetition of standardized trade process increases that productivity and efficiency. Whether it's the on-site application coupled with the off-site industrialized workflow, that creates a very lean environment. And so the predictability of the deck time and cycle time of that deck raise for us is a very standardized process. And I think Jeff spoke to it earlier in terms of the performance, that learned application of picking up 10 months on SRR3 and SRR4. And so for healthcare and for complex projects like healthcare, those benefits, those realized benefits can be gained on a real-time basis, on an application that can be, that's not subjective. They're measured, they're quantifiable, and they can be dealt with in a planned percent complete application that is very real with your vertically integrated supply chain to know what those metrics are. And so, from all of these, floor level construction, you get some really true time savings. And so those are the maximization that we really look to in terms of performance for a learned process for top down. And so those advantages, I think, are really applicable to how a lean application coupled to a design build solution or a design system, an engineered system, really achieves better maximum value. And as a builder, I think from a building application, you're able to execute more program work, becomes more efficient. And so I think the trades gravitate more to it. Again, there's always that what's new is difficult for our industry, I think, as a whole to gravitate to, but I think it is catching on. So what we're excited about it is all of the benefits below, just in terms of the superstructure represents about 40% of the material by mass, or I should say the embodied carbon. And when we can reduce that structure by 40% of material by mass, we can reduce that embodied carbon footprint. And so the building, by definition, is a more sustainable cost or a more sustainable structure. So the ESG format or footprint is substantially improved. And so I think the benefits overall for the structure have a better time to market, cost footprint, and then a more sustainable footprint. So all of those things coupled together from a delivery standpoint, as a builder, you're able to provide a better product. It's a more sustainable build. It's a more flexible and efficient structure. So I won't kind of go through all of these points. I know that this presentation's a short duration. I want to get to the engineering elements because that's the key basic point. Without the engineered solution in core and shell, you're not able to deliver it with that jacking system, because the jacks make it what it is. I mean, with the jacking system is how you get it up and having no columns. And that's fundamentally the process of the build. For healthcare and integration, a lot of what we do, and I'd be remiss if we didn't add this element to it, is a lot of the vertical supply chain is prefabrication. And so when the decks are constructed at ground level, we integrate a lot of modularity to offsite fabrication and offsite production. And so as the deck is a structural deck element, we floor load that for fit out. And so we have a supply chain partnering relationship with a number of companies that are focused very specifically in the healthcare space. We do work with blocks on some R&D that we're doing. And we also work with Falk Built that does some interior demise space for head wall and both systems and panelized systems for interior fit out, and those systems really allow us to build out inpatient and interior demise space for healthcare, and so that allows us to provide that healthcare layout, and so we're able to provide that system for healthcare is incredibly flexible on planning, interior space planning, and without columns, that flexibility increases exponentially from a design perspective, both architecturally and structurally. So we have a lot of that floor plate becomes a pretty diverse element with live, how healthcare planning works. So, the next slide here. Again, I kind of want to go over this just in very briefly. Talked about a lot of this, and I won't really go over this a bunch, but I think the core element here is this side of the slide, which you really focus on is the entire build is a structural element. Without the inherent design of the structural engineering on core and shell, coupled with the delivery mechanism of the building application, and the vertical supply chain of how this comes together, you have a complete system. But again, it is a learned system because everything is in compression and shear on the core, and there's no net uplift, no columns, and it's delivered through this construction methodology. You have a complete delivered system. And so, getting the entire supply chain of the construction apparatus from design and builders, and especially subcontractors, which the TGE team is obviously engulfed in, is a truly unique and innovative solution to providing a core and shell strategy. And again, we do that for all asset classes, but healthcare, it definitely is a vertical within that supply, or it was within that delivery process. As projects become more complicated, and they shouldn't be, our initiative and focus has always been to lean it out, because we're going from design to manufacturing to fab to construct. And that process is a very simplified process because of the standardization of the build. And this innovative strategy really allows that to take place at a more standardized basis. So we're happy to help with some learning on this and introduce more of it to market and go from there. So with that, I'm going to turn it over to Charlie and let him talk about the inherent structural system of top-down.
Historically, this system was first used in California in mid-1960s. 4 buildings were built in the Bay Area. 1 was built in San Francisco. 1 was built in West Virginia. And the last one is where I got involved in it. It came to New York City. Okay, all those projects are on our website. So we've sort of rode the cycles, okay? In 1972, the inventor came to New York to build a Russian mission to the UN in Riverdale, New York, and then the Arabs cut the oil. So I bought into the system, went to Moscow, Saudi, and Iran, and started designing these buildings in those places. Then the Russians invaded Afghanistan. Jimmy Carter pulled the plug on our 15 projects, and I bought Thornton Tomasetti from a publicly traded company and didn't really look at this until approximately 2005. Our big luck was getting involved with Intel, met Jeff, met Dan. We did the 2 projects. At the end, Dan said to me, and Jeff said to me, "Can I join you? This thing's going to take off like a rocket." So let me tell you about the advantages. We cut things by 20, 25%, 20 to 30%. But it's even more than that. A cast-in-place concrete framed hospital weighs 3 times as much as our system. 3 times. That means 3 times the foundations, 3 times the column area. Okay? It's an amazing system. Our floors are connected together with serviceability posts in the exterior walls that eliminate all vibrations in laboratories such as Intel and all live load, differential live load. Our cores are all in compression. They use ACI minimum steel. They have 80 pounds of rebar per cubic yard instead of 250 in a conventional job. We've got a 34-story concrete building right now. It's 3 times heavier than us. We use 24 piles. They use 75 piles. This is the best system you could ever come up with in terms of saving time and saving money, and it's safe. Am I getting some sort of am I getting the gong show?
No, Charlie, keep going. I think Dan dropped off for some reason, and
okay. So
we'll get back.
The system does. It takes all of the advantages of concrete, all the advantages of structural steel, and it uses them the way it should be used. The core should be in compression with no net uplift. There should be no tensile stresses in the core. Okay. The floor system has no steel added to combat deflection because we tie all the floors together from the second floor to the roof. The whole building is like a big monkey bar connected together, and the loads go in ways that structural engineers have never seen loads go. They don't go up, they don't go down, they go both ways. So it's really a special system. And I'm going to leave some time for questions because Dan and I can go forever on this. Everything we're saying is pretty much on the website. Oh, we took a shot at Jefferson in downtown Boston, downtown Philadelphia, and we did a scheme with Suffolk Construction out of Boston and now Philadelphia. Then we went to Mass General in Boston, and we did another scheme. And we're now looking at a whole bunch of different projects. I mean, Intel was 90 by 300. That's exactly the dimensions of a typical hospital with a 90-foot width. Doesn't have to be. And that was 13 pounds of structural steel per square foot. And when we closed the deal with Intel, I said it's 13 pounds a square foot. They said it better be. And it was, exactly.
Hey, Charlie, we've got one question on the line here. And the question is the design of the floor plate limited, or do you simply build more cores?
Intel was 7 cores. Edmonton, Canada is 1 core. Wauwatosa, Milwaukee is 1 core. Rhino Rise and Evolve in Denver are 2 cores. Dan and I added it up yesterday. We got $1 billion worth of work in our pipeline. No hospitals yet.
Yeah. The core dynamic is going to be dependent upon, obviously floor plate and cantilever distance, and that's really the only constraint is your cantilever distance and the layout of the requirement and then live dead load analysis. But the constraints are dependent upon design, but the flexibility and the utilization of the design is anything you can build conventionally, you can build with top down. The only constraint is location, where you want to put the core, or is there a core constraint? And what is your cantilever distance or edge of deck to face a core?
Let me give the cantilever dimensions, okay? In a hospital, it could be 30 feet, it could be 35 feet. We have solutions for that. In office buildings, it could be 45 feet. In residential buildings, high end, 25 to 30 feet. Middle, 18 feet. Student housing, 15 feet. It's all about keeping the cantilevers reasonable, keeping the core reasonable. But it's a balancing act by the structural engineer who's designing it, because you got to find the balance between the size of the core and the size of the cantilever. And we go through about 3 passes, and we get it absolutely within about 5% of the quantities after about 5-10 days of work. It's so predictable.
The other thing is the core is usable space as well. So it's not limited. It's not non-usable space. The core can be utilized as interior space planning.
This is Mass General. You can put patient towers on the top of the more hospital suite stuff on the bottom. This was a design that was done by somebody, and Suffolk sent it to us, and we said, this is what we would do. I'm not sure what happened because this was all at the beginning of COVID, and I have a feeling that neither Jefferson nor Mass General has actually happened. We did the Hopkins project. That was $1 billion. We weren't doing top down yet, but we could have. We've got modular hospital designs. We've got a deployable 56-bed hospital that you can put on a barge and send anywhere in the world on the waterfront. We don't stack modules, we slide them onto the floor. So stacking boxes is the stupidest way to build a building, because after you stack 16 boxes, you got to put a 5-foot thick slab at the bottom of it to hold them all. We slide it on the floor, slide it right on the floor. And we have patient room modules, and we even have OR modules. So it's a very, very flexible system. Caesar Pelli has done a bunch of designs for us, and most of them are curved. We can do curved plans. We can do zigzags. We can do almost anything. And when the architect first gets involved and realizes there's no columns, they really like it.
Say, Charlie, this has some other advantages in a dense urban environment. Could you maybe comment on some of the advantages in an urban environment using this system?
Well, we've got some 70 by 100 foot sites in New York City that we've done intercontinental hotels on. And you know, when you got lot line windows in a large city, it has some other issues depending upon where your site is. But yeah, no, these are all needle towers and they really work really well. We've got high rise. We've got one design in Chicago that's 100 stories. And there's no net uplift on the core. That's amazing. We've got a design. I'm working on a study of what could have been done at the World Trade Center, and we're using TGE to design a building that if we were in a position to rebuild it the way it was originally, we could do it, and guess what? It wouldn't collapse. Very flexible. Any more questions?
Say, Jeff, one of the comments you made, there's a lot, change is often difficult to accept, and I think that's probably more so in the construction industry. Can you comment a little bit on how, as an owner, you were willing to accept this change and take on this opportunity?
It was really driven by need. So, I mean, sometimes you get pushed into it, but the companies I was working with, again, because they were innovation type companies, we were pushed pretty hard, and it came down to like any decision you make. We looked at the risk first, the benefits, and a lot of it came down to Charlie Thornton, right? We looked at it, our internal people. We had our own internal structural people, and some of those that said it wouldn't work. And I said, if the guy who did the engineering for Petronas and Taipei Towers could make those stand, I'm sure he could make this stand. So there's always those naysayers inside the company, but when they saw the benefits of this, of truly doing construction half the time, when the business groups got to go in and deal with, they were always complaining about their labs around vibration limitations that we could give them on multi-story buildings and the use of the space, the columns or how we could set their labs up and so forth. So when we lined up all the benefits to people, the benefits just outweighed, what the perceived risks were at the time. And for us, the risk item was a much bigger category because, again, like Charlie said, it hadn't been built in 40 years, right? It was something it had been done, but it was a long time back. It wasn't that it was going to be structurally infeasible, but could we adapt all the latest technologies like pumping concrete, slip forming, some of the latest methods around steel and the CNC? We didn't know if we could get all those benefits. It's now been empirically proven, so to me, from an owner, to go back at this stage and go show, now what the risk is, where it's greatly diminished because the empirical proof is there. The benefits continue to increase, as Charlie, like you said, is continuing to design platform and portfolio on how to expand the use of this. So I think that was it, Edwin. It was really just the benefits versus the risk.
I'm going to tell everybody what you said to BK, Jeff. If it doesn't work, fire me.
I'm gonna answer a quick question that I see on there. How are the floors lifted? I see a question there. So on the screen right here, what's on the top? There's no tower crane. So the instead of jump forming the cores, we slip form the cores. So cores are slip formed at one time. So they're at final elevation, and we attach strand jacks at the top. So at the top of this, it's kind of a tough picture to see, but strand jacks are fixed at the top of the core, and then you have a cable that's run down to the bottom of the, obviously and connected to the deck plate. And so that's done at the top of every core. And so these jacking systems affixed to the deck plate, and then they're jacked. And so this jacking system raises the deck. And so if I run this in the time lapse, what you see is this deck, which is now the roof, actually being lifted. And so you see this lift. And what happens is there's a connection point where this deck is now locked into the core, and the deck is locked into the core in compression and shear. And so imagine a giant cotter pin. So what had happened is this structural membrane or structure member is now locked into the core, and this is one assembly into the core, and it's again in compression and shear. So this unit is now a complete unit into the core, and so it's a rinse repeat. So now what you're seeing is this jacking member or this strand jack being reassembled and rinse repeat. So it's coming back down and being reassembled just like all these other R's, and being relifted back into the core to be done again. So a highly repetitive system, again, the learning curve on it is systematic. As Jeff mentioned earlier in his first part of his piece on the SR3, SR4, 10-month productivity increase from R3 over 1. So the learning, as far as from a dedicated crew, from going to one to the other. But if we were just to look at the metrics on the pro forma of a program of a conventional build of 36 months, conventionally speaking, to do this building conventionally, to what we actually built that project for at 22 months for the first building, substantial time savings from top down to conventional. So, and then to take the performance of that second building to the first of another 10 months of a delta is significant. So I think those are the metrics that I think that we look at when we look at the performance of the efficiency ratings of looking at how productive this system is relative to looking at it as a comparative analysis to conventional construction, and then how we lean out if we can get that team to go and do the next building in the same fashion. So, but that is in essence the lifting mechanism and the process.
So we got just a minute or two, and Charlie, there's one last question here that says, during construction and with a few floors lifted to the top, what are the concerns about seismic safety or seismic activity?
None. It's all taken care of in the design. And think about wind and think about seismic, okay? This building is designed, that's on the screen right now, for 10 stories. If you got 2 stories up at the top, your mass and your wind area is 20%. There's no problem with an earthquake. This system is so light. That's all engineered by the structural engineering team. We are a means and methods design firm. Every other engineering firm in the United States doesn't do means and methods because their lawyers and their insurance companies have said, you don't help the contractor. This is a design build method, and you have to be involved telling everybody how to do it. And nobody else in the United States engineering community does that, and that's why they all suck. Sorry. Talk to a contractor. Do you get any help from an engineer when you need help on means and methods? No, they won't touch it. Talk to my son, who just finished the Las Vegas football stadium. Enough.
Thanks, Charlie. Well, I
get passionate.
That comes out, and I think, hopefully you can come away from this presentation. We'll wrap up here with a feeling for the innovation and how this is a totally different perspective on how to look and build, and the savings and advantages that can come from it. Thank you very much for your time.